turn raw labels, clicks, and features into training data for LightGBM ranking. This is the pattern you'll be able to implement by the end, which turns judgments and clicks into labels and packs grouped features for ranking. I'm Professor Pi, teaching search and IR with simple Python. Preparing data for a learning to rank model is often the hardest part of a search project. Labels are messy. Labels are messy. Clicks are noisy. Editorial grades are sparse. Success means a clean matrix of feature vectors, a single label per query document pair, and a clear grouping that tells LightGBM which rows belong together. Do this right, and a modest model can reorder results toward real user value. At its core, we want to combine human judgments and behavioral signals into a graded label, attach features per pair, and tell LightGBM how many documents belong to each query. Imagine 3 documents for query Q1, with an editorial grade for 1 and click counts for all 3. We want a small numeric grade for each pair that LightGBM can learn from. The strength is practical and fast training. The weakness is that choosing how to merge signals changes which documents get boosted. We will build a compact pipeline that converts mixed signals into labels, builds an LGB dataset with groups, trains both pairwise and listwise objectives, and packages this into a reusable builder. This keeps the code readable, and the mapping back to document IDs simple. Now we will merge judgments and clicks into a single graded label. This snippet converts mixed supervision signals into a single graded label per query document pair. The dictionary judge holds editorial relevance grades, and the dictionary clicks stores observed click counts. The variable labels merges them with a simple additive rule that caps click influence, which avoids pathological overweighting for very frequent documents. The key idea is to preserve editorial intent while still letting behavior shift relative ordering in borderline cases. You can adjust the 0.3 factor to make clicks contribute more or less to the final grade. Higher values trust behavior more. The printed y_Q1D2 value confirms a concrete label that downstream ranking will learn from. Next, we will assemble features and grouping for LightGBM. This example assembles LightGBM-ready training data with query grouping and explicit feature names. The dictionary feats maps each query document pair to a compact feature vector, representing signals like BM25, document length, and a neural score. The list pairs fixes a deterministic ordering of pairs, so X and Y align exactly. The list QS extracts query identifiers used to compute the group list, where each value is the number of documents for a query as required by lgb.Dataset. The call to lgb.Dataset builds an in-memory dataset with labels and group structure attached. The printed groups and rows verify the expected query blocks and total training instances. Now we will train a pairwise LightGBM ranker and inspect predictions. This code trains a pairwise LightGBM ranker and inspects its top prediction for a single query. The dictionary params selects the rank pairwise objective with an NDCG metric, a fixed seed for determinism, and modest tree capacity. The call lgb.Train fits the model on the grouped dataset train, returning a booster. The vector preds holds per document scores from booster.predict for our original X ordering. The list IDX gathers positions corresponding to query Q1, and the expression with max selects the index of the highest score within that query. The printed top Q1 shows the model's current best document, which is the central ranking action we care about. Next, we will switch objectives to a listwise LambdaMART setup. This snippet switches to a listwise LightGBM LambdaMART setup, and reevaluates the top document. The list yInt discretizes the labels for well-defined gains, and the dictionary p2 activates lambda rank with an explicit label gain vector emphasizing higher grades. The object train ls is a fresh lgb.Dataset using integer labels while preserving group structure. The call lgb.Train fits the listwise model, and booster predict returns new scores in preds2. The index set idx2 isolates q1's rows, and the max operation selects the current leader under the listwise objective. If you increase label gain spread, the model prioritizes highly relevant items more aggressively. The printed top document reflects objective-sensitive ranking behavior. Now we will wrap the assembly into a reusable builder function and run a final check. This example packages assembly into a reusable function that returns features, group sizes, and the aligned pair ordering, then applies the listwise LightGBM model. The function build LGBM ranking enforces a stable ordering over query document keys and derives group counts from the query identifiers, producing a consistent training or inference layout. The tuple returned includes pairs, so we can map back from row indices to document identifiers. The call model ls predicts scores the freshly assembled matrix x2, and the generator expression selects q2's rows before choosing the highest scoring index. This compact pipeline step shows end-to-end readiness. The printed top q2 pipeline confirms the function feeds the model correctly. In a real project, you would swap the toy BM25 and neural scores for your production signals. The same builder accepts those additional columns and keeps the mapping from model rows back to document IDs intact. That makes evaluation and online debugging straightforward. Recap: what we built, when to use it, and one caveat. What it is: a small pipeline that merges editorial grades and clicks into graded labels, assembles feature matrices, and builds LightGBM gripped datasets. When to use it: when you have mixed supervision and you need consistent grouping for training pairwise or listwise rankers. One caveat: how you weight clicks versus editorial labels changes model priorities, so test gains on held-out queries. Next step: tune the label gain vector and measure NDCG on a validation set to see how stronger gains change top result quality. If practical, hands-on IR tutorials help you, subscribe and watch the other IR videos.